name is Isabel Kühner, and the topic of my talk is swarm intelligence for solving a traveling salesman problem. Our motivation is that we want to play the board game Halma, also known as Chinese checkers, which is a game for 1 to 6 players. The goal of the game is to get all game characters from one corner of the board to the other, so to the opposite corner. And by doing so, you use the nodes that are connected by the edges. And the goal is to find the shortest distance to get from one corner to the other to win the game. And as we have those nodes and edges and we want to reach the shortest distance, we have similarities with the traveling salesman problem. As it is not possible to solve Halma analytically, and we have several game characters per player, we thought about swarm-based algorithms to solve the game. Swarm intelligence algorithms are based on animals that live together in swarms. They cooperate, for example, to coordinate their food searching process, and they divide their tasks. They communicate either directly or indirectly over the environment. To find the good solution to play Halma with swarm intelligence, and because the Halma board has similarities with the traveling salesman problem, we first tested the approaches for the traveling salesman problem. And this I want to present in this talk. Later, we can also use the approaches from the Halma game and the algorithms we use there for swarm robotics, for example, and swarm of drones that is used for disaster management. First, I want to shortly summarize the traveling salesman problem. So we have a salesman and wants to visit a predefined number of cities. He wants to visit every city only once, and his starting city is only the end. It's also the end. The distance between the cities is different, so each link has a different weight. And the salesman wants to reach the shortest distance to collect all cities. Testing all solutions to find the shortest distance is time-consuming or infeasible depending on the number of cities, because the number of solutions is a factorial of the number of cities. That's why you need algorithms to solve this problem. The 3 swarm-based approaches I will present in the following are the ant colony optimization, short ACO, the particle swarm optimization, PSO, and the bee colony optimization, BCO. I will start with the ant colony optimization. So this algorithm comes from the food searching process of ants. Ants leave pheromones on their way, so they communicate indirectly over the environment. In this simple example, we have an ant nest on the left and a food source on the right. There are 2 possible paths to get from the nest to the food source. One path is shorter than the other. In the beginning, the ants will choose their path more or less randomly. And the ants that will choose the short way will reach the food source earlier. On their way, all ants will leave a pheromone trail. So when the ants arrive at the food source from the short path and they want to go back, they decide, depending on the pheromones, which path to choose. So they choose the path with most pheromones. And so as the other ants haven't arrived at the food source, the ants will choose the short path. If then the ants arrive that chose the long path, they will also choose the short path because there are more pheromones and more ants will choose the short path. And as you can see in the animation, the more pheromones on a path, the darker the path gets. And if you would iterate this algorithm multiple times, in the end, all ants will choose the short path to reach the food source. As an algorithm, we have first the initialization, and then each ant plans a path either on exploration or exploitation. Exploration means to find new path, and exploitation means that you exploit an already good solution that was found in the path. So if the ants choose exploitation, they build their path depending on the pheromone values on the edges. If they choose exploration, a random proportional rule is applied. So the edges are chosen more or less randomly. After each ant has constructed its path, the local update is conducted. So pheromones are added to all edges that were visited by the ant. And then the global update is conducted, so the global best path is searched, so the best path that was found by the swarm in this iteration, and extra pheromones are added to all edges that are part of this path. To avoid getting stuck into local minima, there is an evaporation. This also happens in nature, for example, because of wind. And then the algorithm is iterated multiple times. The second algorithm I want to present is the particle swarm optimization. It comes from bird flocks of fish schools. So if you imagine a bird flock, they seem like they're moving as one individual. So the individual birds of the flock orient on the other birds how they should move. And this is the concept of the particle swarm optimization. So if we, for example, focus on the red bird in the middle, this bird builds a path for the traveling salesman problem. And also its neighbors, so the other members of the swarm, build a path for the problem. And as I mentioned before, the members of the swarm orient on their neighbors. And this orients on an adaptive culture model, which says that an individual is able to evaluate, so to determine if something is good or bad. It is able to compare, so to compare its own results with others. And it's able to imitate, so it's able to imitate the behavior of a superior neighbor. So let's focus on the red bird and one of the black birds. So each of the birds constructed a solution for the traveling salesman problem. And we have the cities, so we have the order of the cities for the red bird is, for example, A, C, E, B, D, A. And the black bird chose A, C, B, D, E, A. We assume that the black bird has the better solution. So the red bird tries to adapt parts of the path of the black bird. So for example, the black bird chose B as its third city. So red tries this as well and swaps B with its current third city. And a new path results from this. So now the red bird has the order A, C, B, E, D, A. If we would swap more than one city pair, we would call it a swap sequence, which is a basic concept of the particle swarm optimization for discrete problems. Yeah, so for the algorithm, we have in the beginning the random initialization of the path, and we also generate randomly a swap sequence. And this swap sequence is called velocity. This term comes from the history of the particle swarm optimization and the first particle swarm optimization algorithm where a real bird flock was simulated. So we had really the movements of the birds here and they really moved and we had really a velocity. So for discrete problems nowadays, it's only the term velocity and you just use the name for describing those swap sequences, although it's no real velocity. So the swarm member can then decide if he wants to include the personal best path. So the best path is it has found in the past. And if he wants to do that, he creates a swap sequence from its current path to the personal best path. And this swap sequence is then combined with velocity. The individual can only include the global best path, so the best path that was found in the past by the whole swarm. And also it can then create a swap sequence from its current path to the global best path and then combine this with real velocity. Then this velocity is applied to the current path and a new path is created by doing all the swaps. And after that, the personal best path and the global best path are updated depending on the distance of the path. We have for this algorithm an exploitation because the personal best path and the global best path are considered. And we have an exploration because the path is changed in every iteration because we consider the global and the personal best path and combine those swap sequences. In contrast to the uncolony optimization, only the best solution of the past is stored and not the whole history, as we have for the uncolony optimization where we have the pheromone values. The last algorithm I want to introduce is the bee colony optimization, short BCO. It comes from the food searching process of bees. So bees fan out of their hive to search for food. So they construct a path of the traveling salesman problem. And then they return to the hive and dance to the other members of the swarm to communicate their solution and their findings. So they advertise their solution. The other bees can then decide to either abandon their solution and take another bee's solution, or to choose their own solution and dance. So for the bee colony optimization, in contrast to the other two algorithms, we do not construct the path for the traveling salesman problem as once, but we have several stages to construct the whole path. So in each stage we construct only a part of the path. And then in each stage we have two steps, the forward pass and the backward pass. For the forward pass, the bee builds a part of the path randomly, and this is our exploration. Then the bee returns to the hive, and it can decide in the backward path to either choose exploitation or exploration. So to abandon the part of its path and take another bee solution, which is then the exploitation. Or it can use this explored solution it created in the forward path and advertise its part of the path. And then after completing all stages, the whole path is constructed, and also the global best path is updated. And this global best path can also be used in this exploitation step of the backward path. So if the bee abandons its path, it can not only choose a part of another bee, but also use the global best path to construct its solution. So we have the similarity with the particle swarm optimization that we also remember the global best solution. And as I mentioned also there, it's a difference to the uncolony optimization where we remember the whole history. So we did several tests for the 3 algorithms and the traveling salesman problem. And we had a traveling salesman problem with 10 cities. And we iterated every algorithm 200 times. And we did 1,000 tests per algorithm. And in the diagram, you can see the ant colony optimization in blue, and we tested it with 100 ants. The particle swarm optimization in green with 50 elements, and the bee colony optimization in red with 100 bees. And in the black line on the bottom is the optimal solution of the traveling salesman problem. So for the ant colony optimization, we had a parameter to define the balance between exploitation and exploration. And we had 80% on exploitation and 20% on exploration. And you can see that the swarm converges towards a relatively good solutions in comparison to the others. And for example, we have here one experiment with where we had 100% on exploitation. And as you can see that the swarm converges very, very quickly, but towards a non-optimal solution, so it gets stuck into a local minimum. This shows us that the balance between exploration and exploitation is very important for those algorithms. For the particle swarm optimization, which is shown in green, the path length decreases constantly with the number of iterations. So we have an effective balance between exploration and exploitation. And this algorithm may have performed better with more time, but we limited the number of iterations. The bee colony optimization in red decreases rapidly, but towards a non-optimal solution. So exploitation predominates over exploration. But the advantage of the bee colony optimization is that there are only a few parameters you need to tune. To summarize the advantages and disadvantages, the ant colony optimization converges for a small number of iterations, and we have a parameter to control the balance between exploration and exploitation. A disadvantage is that you have a lot more parameters that need to be tuned. For the PSO, we have a good balance between exploration and exploitation, but the algorithm needs more iterations to converge. And the bee colony optimization has only a few parameters, which is good, but on the downside, exploitation predominates over exploration. So for our experiments, the ant colony optimization performs best for the traveling salesman problem. And it includes all solutions of all iteration and weights them, and does not only keep the best ones in memory. And we also saw that the balance between exploration and exploitation is very important. So for our Halma board game, we want to combine the swarm intelligence algorithms to play the board game. So we want to choose the ACO for path planning because it performed best for the traveling salesman problem. And as we have several characters, but we can only move with one at a time, we want to combine it with the bee colony optimization to find a consensus which path to choose and which character is allowed to move. And later, these concepts can be applied to swarm robotics to use drones for disaster management. This was my presentation on the topic swarm intelligence for solving a traveling salesman problem. Thank you for your attention, and if you have any questions, please consider contacting me.